Okay, so we're going to talk about the beauty of math. So many patterns and sequences can be found in math. These math patterns can also be found in nature. Many of these patterns were discovered many years ago. So you can either stop this video now and go watch the Donald Duck in Math Magic Land, or you can watch it at the end. The key thing I want you to pay attention to is you can start at 2 minutes and 40 seconds and go to 13 minutes and 45 seconds, or you can watch the whole thing. If the link that I provided you in D2L does not work, just type in Donald Duck in Math Magic Land in YouTube and you will be able to find it. I actually enjoy watching it each semester, so you might find that it's kind of fun. It's not just mathy math, it's actually very interesting about the history of math and some of the things that we know and love today. So Fibonacci was a very famous mathematician, still is, and he lived a long time ago. And in 1202, Leonardo of Pisa, also known as Fibonacci, wrote a book, Liber Abaci, where he introduced Hindu-Arabic numeration system to Europe, and that's the same number system we use today. He was trying to explain the new system in order to replace the Roman system of numeration for doing calculations. He included the following problem, which is perhaps the most famous sequence in the history of mathematics. It's called the rabbit problem. Assume every pair of baby rabbits will mature during their second month and produce a pair of baby rabbits during their third month. If we place a single pair of baby rabbits in a pen, how many total pairs of rabbits will there be in the fifth month? Assume that once adults start producing babies, they do so every month from then on. So here we have our first set of baby rabbits. And that pair of baby rabbits is put in the pen in the first month. In the second month, they become an adult. Once they're an adult, they become eligible to have babies in the third month. So in the first month, we have one. In the second month, we have one. In the third month, we have one adult and one baby. So we have two pairs. In the fourth month, we have the original adults, we have the babies who became adults, and those original adults had another set of babies, so we have three. In the fifth month, we have the two sets of adults that we already had. This set of babies become an adult, and these two adults had another set of babies. So we have one pair, two pairs, three pairs, and five pairs. So the growth of the rabbits leads to the Fibonacci sequence. If we count the pairs of rabbits each month, we find the following sequence of numbers. So one pair, two pairs, three pairs, five pairs, 8 pairs, 13, and 21. And there's a pattern that emerges. If we add the first two numbers, 1 plus 1, we get 2. 1 plus 2, we get 3. 2 plus 3, we get 5. And we're kind of following the math down here. 5 plus 8 is 13, 8 plus 13 equals 21, and so forth. The Fibonacci sequence is seen in many living organisms. Some plants form branches that follow a Fibonacci sequence. So they start with the original stem that has a branch off, and you have 2. Then you end up with 3, and 5, and 8, and 13 as it continues to branch off. The number of petals in various flowers are Fibonacci numbers. The iris has 3 petals, the buttercup has 5, the bloodroot has 8, and the black-eyed Susan has 13. The number of sections in many fruits are Fibonacci numbers. So we have 5 of them that have 5. Here's an apple. We've got bananas that have 3, and the grapefruit has 13. The spiraling pattern in dahlias, pine cones, and sunflowers show Fibonacci sequences. The pine cone and the dahlia have spiraling arms of 13, and then here's our sunflower. Fibonacci numbers are seen in animal bodies as well. So we have the sea star, the sand dollar with 5. There's another sea star with 13. Humans have 5 fingers and 5 toes. And the lengths of the segments of each finger follow the Fibonacci ratio of 3, 5, and 8. Let's talk about the golden ratio. If we take the numbers from the Fibonacci sequence and divide the numbers from the previous by the previous number, so we had 1 divided by 1 equals 1, 2 divided by 1 equals 2, 3 divided by 2 equals 1.5, 5 divided by 3 equals 1.67, 8 divided by 5 is equal to 1.6, 3 divided by 8 is 1.625, and as we continue on, when we get to 55 divided by 34, we get 1.618, and so do all of the numbers that follow that. So it appears that the numbers go towards a fixed number, and they actually do. 200 years ago, it was proved that they approach the square root of 5 plus 1 over 2, which actually is 1.618, and called the golden ratio. So the golden rectangle has one side that is the square root of 5 plus 1 over 2 times as long as its other side. The ancient Greeks believed that any rectangle like this was perfectly proportioned. They used these golden rectangles in designing the Parthenon, which is this building here, and the modern architects use golden rectangles in building the United Nations building, which is here. And you'll see both of those in the Math Magic Land with Donald Duck. So here we have the golden rectangle. So this whole entire thing is a golden rectangle. If I remove part A, then this is still a golden rectangle. If I then remove part B, this bottom portion is the golden rectangle. If I remove C, this is now the golden rectangle. And if I remove this square, I still have a golden rectangle. And we can continue on with that. So this is talking about cutting off a square off of each of those parts, leaves us with a golden rectangle. Now, if we then create a smooth curve on each of those squares we are cutting off, we can create a spiral, which is called the golden spiral, and it forms a shape like a chambered nautilus. So if we, on each of these squares, or these rectangles, we do this and connect from point to point, we can create the generated golden spiral. And it occurs in nature in several ways. Here's a hurricane. Here's the solar system. This is a cornucopia that we see in the fall. And in November, on the 23rd, it's Fibonacci Day because it's 1, 1, 2, 3, the first 4 numbers of the Fibonacci sequence. Here's a chambered nautilus, and this is what it looks on the outside. It is a mollusk that lives in the open waters of the Pacific Ocean, and it looks just like it on the inside, and it uses the chambers for buoyancy. Now, in your D2L, you have this document to create this project. So what you're going to do is print off the document, and I've written out instructions in there as well. You're going to start with the red square that is already pre-drawn. It is following the Fibonacci sequence here. So we have 1, 1, 2, 3, 5, 8, 13, 21, and 34. So the red one is the first one, and I've drawn that for you. You're going to go above it and draw a square right above it. Then come over here and draw a 2 by 2. So you're looking at 2 squares this way and 2 squares that way. Below it, you will draw the 3 by 3, and then to the right, you'll draw the 5 by 5. Notice how all of the lines match up, and you're making golden rectangles there. Above it, you will do 8 by 8. So that means you're going to count 1, 2, 3, 4, 5, 6, 7, 8, and then count over 8 this way, and that should create this square. If you count over 13, you should hit the edge of the paper, and you're going to count down 13, and it should match up here. Then count down 21 and count 21 over, and it should count straight up. You will end up with some extra lines down here, so don't worry about that. And then you're going to count over 34. You should have some lines left over here, probably not as many as you see here, and it'll go up. You do not have to write those numbers. Those are there for you to understand that that's what you're counting. After you get it counted and drawn, you're going to start from this corner and draw a curved from one point to the next. So curve here, curve there, curve there, curve there, curve up, curve around, around some more, come down, come up to this corner. This is off a little bit, but come up to this corner and then come back here somewhere. Don't care exactly where. Once you get it all drawn and you do your golden spiral, I want you to decorate it. So get creative and decorate your golden spiral. You can do something like this. You can do something like this. Now, I can't draw anything like this. These are drawn from previous students. So this is a hummingbird with a flower. We've got a bug. We've got the turtle walking along the waves here. We've got some yellow with some flowers there. Anything you want to do. You can do just stripes. You can do a checkered pattern. You could do something in blue and gold for the school colors. You can do anything you want. If you color it and do anything with it, you'll get your good grade, as long as everything is on your matching on your squares and stuff. And you can see how the other students have their squares going along. So yours should look something like this underneath there. If you get creative like something like this, or creative in any way where it's not just plain color, you can get bonus points for being creative. So you will then follow directions on D2L on how to submit this.